Okay, so share notes. Uh, Okay. So yeah. Um, we'll just speak for some time and then get going. This is the second class on statistical mechanics, and I'm sorry, I'm a TMR fellow from IISc, and this is a TA course that I'm trying to do as a part of TMRF TA requirements. Okay, so we'll, I don't know, this got stuck or something. Okay, it seems like it has got. Mm, okay, I hope it works. Okay, so we'll just wait for a couple of minutes and then get started. Okay, so if I have to, quickly talk about what we had discussed in the last class. So the last class was a very introductory class where we started with the basic definition of, thermodynamics and statistical mechanics and the basic idea of equilibrium and how these two pictures, like the macroscopic thermodynamic picture and the statistical understanding, which is more probabilistic, how these two are interconnected and related, and like why this connection is so important, which comes up in this statistical mechanics, right? Connecting the microscopic description with the macroscopic variables. So we did discuss about all that, and then we moved towards thermodynamics, which is the phenomenological description of the macroscopic world. And there we looked at the different laws of thermodynamics, what they imply, how the different state functions can be defined, starting from, the temperature from zeroth law, the internal energy from first law, entropy from second law, okay? And what information do they give us about the physical phenomena? And then what's the relation between these different variables, so if you know one, how can you find the others? Okay, the very idea of partial differentials and why they are important. So these were some of the things that we had discussed in the last class, right? So if I have to talk about how we'll proceed in the see this TS session today, is similar to what we have been doing in the last class as well. So we'll talk about some basic concepts, some formulae, some ideas and relations. Okay. And then we'll solve different questions. And if there are any questions from your side, we'll also try to address them and solve the doubts. Okay. Problem solving will be a major part of this session, along with, you know, revisiting certain basic concepts. Now, talking about basic concepts, this is something which we have discussed in the last class as well, right? So, the definition of first law, which actually talks about the conservation of energy, which says that, if there is a increment of heat dq, that can result in an internal energy rise dE and some work done, which is given as dW. The minus sign is a convention which talks about whether work is done on the system or by the system, right? And then we did discuss about the different response functions, which talks about how your system respond, under different conditions. So if you add a certain amount of heat, what is the temperature rise at constant volume? That is specific heat at constant volume. Or what is the temperature rise in, you know, this information of how much temperature rise is associated with how much heat increment. When the pressure remains constant, then it becomes specific heat at constant pressure. So there are all these different response functions which helps us define how the system respond to different changes in this thermodynamic variables. So some of them are also the compressibility or expansivity of the gases, and we defined this quantities in the last class. So we'll see that in many cases these are certain things which we can measure. You can see what is the temperature rise while you keep the volume constant, while you keep the pressure constant. So you can measure all those things, and from there you can actually get to quantifying factors or variables like entropy or things which you cannot directly measure, right? It's difficult to measure. What do you mean by measuring entropy, right? So you have to measure it through certain other variables, and what are the relations that relate the two. Those are certain type of questions that we'll try to address in today's class. And then on the second law, we had this very idea of the Carnot engine, reversible irreversible processes, and then this very idea of entropy. Okay, and this is how it's related. So now with this basic concepts in mind, let us go ahead. So we'll first try to solve a question like this. So this actually brings forth the very picture of polytropic processes. There can be different processes: isobaric, isothermal, isochoric, adiabatic, right? But all of them can be generalized into a form of something like a PV to the power n equal to constant type of equation of state. And these are called polytropic functions, or polytropic processes, right? So for this kind of processes, how do we derive the expression of heat absorbed, or how do you define the expression of work done, right? So that is something which we are trying to do now. So it is saying that we'll start from the first law of thermodynamics, and we will try to derive the expression for heat absorbed in different kinds of processes. Okay, isobaric, isothermal, isochoric, and adiabatic. Now, so what does isobaric process mean? It means that P will be here, P is constant, right? So what it means is that if you compare it with this form, this n has to go to 0. So anything to the power 0 is 1. So that would give you P equal to constant, right? So in this process, n goes to 0. For isothermal, we already know PV equal to constant. This is considering ideal gas, okay? So PV equal to constant. So that means here n is equal to 1, right? For adiabatic, we know it's of the form PV to the power gamma equal to constant. So in that case, your n will be nothing but gamma, right? And there are important relations of gamma with specific heats and all that. Gamma equal to Cp by Cv and all those kind of relations, which comes quite useful, becomes very useful in solving questions. For isochoric process, what does that mean? V is constant, right? So for this, you can imagine. So you can imagine n to be infinity. I mean, whatever the value of n be, however large, this is still constant because your v is constant. So here n goes to infinity. So that's how you can characterize all these different kinds of process into a same generalized form called the polytropic processes, right? Okay. So now, based on the different processes, you can choose different n, right? Now, how do you solve for the expression of heat? That's the question, right? So PV to the power n equal to constant. So these are the different values of n for different processes. Now, what is the expression of heat absorbed? We know from the first law, can write dq is equal to cv dt plus p dv, right? So here cv dt is nothing but du, right? Cv is nothing but du dt. So you can write as dq equal to cv dt plus p dv, right? So if you just replace p from this expression, considering this constant to be some constant a, then this is a typical integration, right? So pv into tf minus t1 plus pi vi minus pf pf by n minus 1, right? That's for any value of n. Normally, this is the form. But there are certain what do I say? So here, if you see, so suppose if you put n equal to 1, what would happen? You would have this terms, there's a 0 in the denominator, right? So it is actually not, this form is not correct for n equal to 1. It's correct for other values of n, not for n equal to 1. Why? Now, if you directly put here n equal to 1, you get a dv by v form, right? And the integration of dv by v gives you a logarithmic term. So for n equal to 1, it takes up a form something like this. For other values of n greater than 1, it would have a form like this, right? Like pv equal to rt. There you have to, you know, you just cannot have this form, okay, for n equal to 1 because this is undefined. So there directly to the integration, putting n equal to 1 here, which will give you the logarithmic description expression. Now for an isobaric process, what happens? Your p is constant, right? So if your p is constant, what you can do, you can directly actually, you can do two things. First is you can also put n equal to 0, right? So if you put n equal to 0, you would get a form like this. There you use the relation between Cp and Cv and R. We know that for an ideal gas, Cp minus Cv is equal to R, right? So you can use that relation, and from there you would get this form. So this is an expression of heat absorbed for an isobaric process, right? Or otherwise, you can also consider the fact that you take P outside and then do an integration, so only the volume would be changing, and then you have to also do certain changes in the expression, like pv equal to uh like p equal to constant kind of form, and then use that, so you'll get this expression. For an isothermal process, this is what we get, right? Now because it's isothermal, now considering the, so if it is a process where the temperature is changing, this is the generalized form, putting just n equal to 1. But now, when n is equal to 1, it signifies the isothermal process, right? So that means Tf equal to Ti. So this term would go to 0. So ideally, you would get this form for your heat absorbed for an isothermal process, where the initial and the final volumes are specified to you. Now, for an isocodic process, what would happen? N tends to infinity, right? So if n tends to infinity, this term here, this term would go to 0. So you would just be left with the first term, which is this, right? And for an adiabatic process, what do? You put n as gamma, which is Cp by Cv. Okay, so if you do now replace this and simplify it further, you would see that this comes out to be 0, which makes sense that in an adiabatic process, there is no exchange of heat, right? So heat absorbed would be 0. So that's how you can find an expression of heat absorbed for different kinds of processes. Suppose you have said that, it's a isocoric process and the temperature changes from this value to that value. What is the heat absorbed? So then you have to use this relation, right? If for some isothermal process where the temperature is provided to you and the initial and the final value of or the ratio of the volumes are provided, how do you find the heat absorbed? So then you look at this value, right? So based on whatever value you choose, or whatever your process is, you have to choose the expression of your heat absorbed accordingly, right? Okay. Now let us try to solve some question, right? So it says that the pressure on a solid is isothermally increased from Pi to Pf, find the expression for W, which is work done, in terms of the isothermal compressibility. So the expression of isothermal compressibility is provided to you. You have to find, expression for work done while the initial and the final pressure is given, right? So where do we start? Let us like see, you have to make use of this expression, right? Now, what do you mean by work done? We know work done is nothing but PdV, right? For a process where pressure and volume changes are involved, we know that work done is given as PdV, right? Now, in that expression, you have to somehow use the compressibility. So what you can do? So yeah, okay. So for this kind of question, here it is said that we have to find the expression for work done in terms of isothermal compressibility, and this is how isothermal compressibility is defined, right? So now we have to think, for work done, we need W is equal to PdV, right? And we know that the pressure is changing from Pi to Pf. We have to make use of this expression, right? So you can understand you have a del V del P at constant temperature here. So what if you write an expression for del V, okay, and multiply with pressure? That would give you an expression for the work done in terms of the compressibility or the volume or the pressure, right? So, and then you can integrate, right? Do an integration from Pi to Pf. That's the basic process, right? So that means if this is your expression for work done, you go from Pi to Pf, okay? So minus 1 by V del P at constant temperature. So then what do? You do dV equal to minus kT V dP, okay? You have just written dV in terms of dP, V and kT, right? And then you do an integration from my P1 Pi to Pf. So this is the form. Okay. So, just be careful about the definition of the different parameters that are there. So see here, the expression was explicitly provided. In many questions, you might just have a value given that your isothermal compressibility is this much, and your volume of your uh, solid does not change much, and the volume is given as this value. Okay, the pressure changes from this to this. Find the expression of work done when the change is happening isothermally, right? So you have to understand this is the process of reaching to that expression. Okay, so that's how you make use of the thermodynamic descriptions of the different response functions. Okay. Now, this is something which we had, briefly discussed in the last class, and we also did solve certain questions. Not briefly, actually, we did discuss about it. So, excuse me. So, we said that, based on what type of process or what type of system we are dealing, you can choose different thermodynamic potentials. Okay, it can be internal energy, it can be enthalpy, it can be Helmholtz free energy, Gibbs free energy, right? And these are the basic definitions of. So internal energy is nothing but U. Enthalpy is given as U plus PV, where you are dealing with hydrostatic systems involving pressure, volume, and all that. Otherwise, it will be something like J into X. Okay, and then you have Helmholtz free energy given as U minus Ts, Gibbs free energy as U minus Ts plus PV. So these are the different most fundamental or most widely used kind of thermodynamic potentials, right? Now, an important point or important thing to remember is how do we write small changes or differentials of this, potentials, thermodynamic potentials in terms of other thermodynamic variables, right? So this expression du equal to TdS minus PdV, Th equal to TdS plus VdP. Okay, how do we get to these expressions? So it's very straightforward, but you must, be well versed with it that and this is your expression of enthalpy. suppose, and then you take a differential like dH, then you can expand these terms, okay, and these terms will get cancelled. What will remain is a form like this. Why it is important is we have solved different questions in the last class. We'll also solve certain things this in this class. So this relations actually gives us, how we can write the different thermodynamic variables like temperature, pressure, or entropy, volume. How do we describe them in terms of different partial derivatives of the thermodynamic potentials, right? So those are the relations that one can get from these expressions, okay? And one can also derive the Maxwell's equations from here, right? So if I ask how is that done, right? So first is to write variables, thermodynamic variables like Tp, S, and V in terms of the potentials. So if I have to just, take this example, so how will you do it? So you have to expand this, right? So if you consider U to be just a function of S and V, so considering U is just a function of S and V, so you write T as, so what is T? T is nothing but del U del S at constant V, right? Del U del S at constant V is your temperature. Similarly, del U del V at constant entropy will be minus of pressure, right? So in that way, you can compare and write this all of these expressions. So you can write Ts, PV, and all this kind of thermodynamic potentials in terms of this thermodynamic variables in terms of these potentials that you can do. Now, how do you get to the different Maxwell's relations from here? Okay, that's the next question. Because that's important, because in case, it's never a good idea to remember things, right? It's always in better to, actually relate the different concepts so that you can derive them if required. So here, the idea is that this definition, so here internal energy is U, H is U plus PV, F is U minus TS, G is U minus TS plus PV. So this definitions, if you know, how do you find the Maxwell's relations? Okay, that's the question. So here you have to make use of the fact that, okay, so del U del S at constant V is like T. Okay, where is my pointer gone? So del U del S at constant V is T, del U del V at constant entropy is minus P. Now, to get to the Maxwell's relations, the important thing you have to remember is all these potentials, these thermodynamic potentials are exact differentials, because of which the order of derivative does not matter. Okay. So del square U del V del S is equal to del square U del S del V. Okay. That is happening because these are exact differentials. Okay. This is a very important property of exact differentials or state functions. And this is something which is very important. Okay. So now if you know this, what it means is, so you know T and P. This is del S del U del S. This is del U del V. So using this, you can now do a derivative of this term with respect to V, and you can do a derivative of this term with respect to S, right? So what do you get? You get del T del V at constant entropy is nothing but minus of del P del S at constant volume. So this is one of your Maxwell's relations. Okay, so that's how, starting from the internal energy, you could get to one of the Maxwell's relations. Similarly, you start with this expression. Okay, so if you start with this, again you write T and V in terms of the partial derivatives like this. Okay, and then consider the fact that H is an exact differential. So del square H del S del V is equal to del square H del P del S. Okay. And then you would get another Maxwell's relations. So these four different potentials will give you the four different Maxwell's relations. Okay. Okay. Now, why do we need this Maxwell's relations? So this is something we had already discussed briefly in the last class, that there are certain variables which you can explicitly, do an experiment and measure, certain variables which are not directly measurable. So by using these relations, okay, suppose if you want to find, del P del S at constant entropy, how do you do that experimentally? How do you keep the entropy constant, right? Or like, how do you define del P del V at constant entropy and measure it like experimentally? So you have to measure it experimentally indirectly in terms of other things where you can suppose keep the volume constant, keep the temperature constant, or keep the pressure constant, right? So that's much easier to do. So there you can actually try to find the different response functions. Okay. And once you know the different response functions, so suppose T by CV, alpha by K, or 1 by alpha B, all these parameters are experimentally measurable. Now, once you get these values, you can actually trace back this process using the different relations, the cyclic relation and also the reciprocal theorems of partial derivatives. And using those, you can actually get back to this, like you can measure this quantity, right? So in a way, if some values or some response functions or some thermodynamic variables are provided, if you want to find some other variables, okay, some other differentials, in those cases you can use the Maxwell's relations. This is a very mathematical understanding of how useful Maxwell's relations are. Okay, we would later see that it's quite more fundamental than just solving certain uh, numericals. Okay, so it actually explains different physical processes. Okay, so we'll see an example of that. But this is how you can actually use it to find different quantities. Now, important part of this kind of solutions or this kind of calculations is this properties of partial differentials. Okay, partial differentiation, and there are two important things. One is the cyclic relation, another is the reciprocal relation. Okay, so we would briefly discuss about that as well. So these are some of the important relations of partial differentiation. I will not go into the details of it, but briefly, so if you have, some function of x, y, z equal to 0, you can always say that, okay, they're related by a functional equation. Where is my, so you're related by some functional equation like this. So you can write f of xy is equal to some f of xy equal to z, right? So you can write z as a function of x and y. Okay. So this is how your partial differentiation would look like. You can write dx in terms of y and z, or you can write dz in terms of x and y. Now, the important theorem is, this is called the reciprocal theorem. So del z del x at constant y is equal to 1 by del x del z at constant y. Okay, just the reciprocal. Okay, you can go through this step to understand that. And another important thing is the reciprocity theorem, which is more like the cyclic theorem, okay, which says that if you have these three variables x, y, and z, they're related by some function. So del x del y at constant z into del y del z at constant x into del z del x at constant y. This product should give you -1. So this is the cyclic relation that we had actually used here. Right, so del P del V at constant entropy is given as del P del S at constant volume into del S del V at constant pressure. And there's a minus sign, right? So now if you take a product of the three, okay, that will be -1. So that's how you can use the cyclic relation, okay? So these two relations, the reciprocal theorem and the cyclic theorem or the reciprocity theorem, are very important, okay? Whenever you're dealing with partial differentiation. And that will be very much useful when you're talking about questions associated with thermodynamics and statistical mechanics and all that. Okay, so now let us try to solve a question. It says that a given system satisfies the relation del S del V at constant temperature goes to 0. Right? This is entropy, V is volume, T is temperature. Which among the following is true for the system? Now, in the all the options you can see, we are looking for a coefficient of pressure at constant volume. So you need to look at some change of pressure. There's some parameter which talks about changes in pressure at constant volume. Right. Now, in this kind of questions, think of what could be a relation that relates del S del V at constant temperature to some partial derivative of pressure at constant volume. Right. So if we go back, del S del V at constant temperature, you can see that there is this relation here. Right. So if del S del T at constant temperature goes to 0, del P del T at constant volume also goes to 0. Right. This is a direct relation that comes out of the Maxwell's relations. Right. So that already tells you that for this case, your answer should be second. Right. Very straightforward question. So all these straightforward questions can come out. Now, because we were discussing about Maxwell's relations, we did tell that, what is the significance of Maxwell's relations, or what does it do in a very physical problem? What does it stress? Right. So what is the significance? So we see that it can actually describe or explain different physical phenomena. So take an example of a basic, phase transition problem where suppose there's some vaporization of a liquid, okay, or melting of a solid, things like that, right? So all this process, suppose the one that we are talking about, so there's some latent heat involved, okay, and the transition happens at some temperature T, okay, and this latent heat is associated with what is the heat absorbed, right? So you can always write dq as L into dm, where L is your latent heat of evaporation per unit mass. Suppose we are talking about vaporization of liquid, right? So then your dq is nothing but L into dm. Dm is like delta mass, and L is the latent heat of evaporation per unit mass. Okay, so this is your dq. Now the corresponding volume change, because there's a conversion from liquid to gas, there's a volume change associated, and that is given as, so if you take the specific volumes of vapor and liquid as V vap and V liquid, so this term into dm will be the corresponding volume change, right? So now if you want to write dq dt at constant temperature, what do you get? You get L by the difference of the specific volume of the two phases, right? Now this is something which is okay, fine. Now how do we you know how do we use the Maxwell's relations here? So now if we look back and look at one of these the first Maxwell's relation, what does it tell us? Where is my pointer? It tells us del S del V at constant temperature is equal to del P del T at constant volume. So if you multiply both sides by T, you would get an expression which relates that in isothermal expansion, the heat absorbed per unit volume, which is the term in the left hand side, is equal to you are gradually changing the temperature and your vapor pressure is constantly also changing. So the rate of change of pressure with temperature at constant volume, okay, multiplied by the temperature, right, is equal to the heat absorbed per unit volume in an isothermal expansion where the temperature is fixed at that value. Right? This is what your Cauchy-Clapeyron equation is telling us, which is coming from the first Maxwell's equations. Right? So now if we go back to our problem of phase transition, what do we see? So the left hand side, dq dv at constant temperature, is given as L by V vap minus V liquid, right? And the right hand side is T into del P del T at constant volume. So what is this telling you? It is telling you that while you can have a vaporization process going on, where the vapor, the volume changes, okay, based on the specific volumes of the two different phases. There's a change in volume, and there's a latent heat involved. So you can find a heat absorbed per unit volume kind of parameter at that constant temperature where this transition is happening, right? So this is an isothermal expansion, suppose, right? So the left hand side. Now, this tells us that on the other hand, if you keep the volume constant, okay, and the temperature is increased, so the liquid will, evaporate, and there'll be a, dynamic equilibrium established, and gradually what will happen? It will reach a new equilibrium state with a new saturated vapor pressure, right? So now if you take this, or find the differentiation or find the change in the pressure with the change in temperature, okay, at constant volume. So del P del T at constant volume, you would see that T into del P del T at constant volume is equal to L by V vap minus V liquid. Okay. So it is actually explaining physical phenomena of phase transition mathematically by starting with the Maxwell's equations, right? So the Clausius-Clapeyron equation gives us one of the examples of significance of the Maxwell's relations, right? Now let us look at a phase diagram and see how, graphically it comes up very clearly, right? Now if I show you this phase diagram and ask you which of these is the phase diagram of water, right? Okay, let me first move the. So if I ask you which of these is the phase diagram of water, how do you address this? See, in this two diagram, what is different? The slope of this line is different, right? Ignore the curve which is in the line. So basically so this line, right? The slope of this line, that is different in the two phase diagrams, right? What is this slope telling us about? The slope is telling us about the rate of change of pressure with temperature, right? So del P del T, that is the right hand side of the Clausius-Clapeyron equation, which is this, which is present here with the T multiplied to it. So basically this, we know the sign of this is different for the two cases, right? Now, for water, we know that water expands on freezing. So that means as you go from a solid to liquid phase, in a typical, some other medium, as you go from solid to liquid, the volume increases. In in water, what happens? When it goes from solid to liquid, its volume decreases, right? And that is related to the slope of P versus T curve. So here, P versus T curve is positive for any other medium. For this plot, P versus T is negative, right? Now, if P versus T becomes negative, what happens? So that means uh, this term is negative. So this is already telling you L cannot be negative, T cannot be negative. So that means this term is negative. That means the specific volume of the vapor phase is or of the so here in this example it was the vaporization of liquid example. It also holds for melting of solid, right? So for in the next example that we're talking about liquid and solid transition, right? So if del P del T is negative, that means for that case V liquid is less than V solid, right? Which happens for water. For water, the volume of liquid is less than volume of solid, right? At that, like when this transition is happening. So That means this negative slope tells us that this is your phase diagram of water. Okay. So the fact that water expands on freezing turns up in the phase diagram, which also comes up in the Clausius-Clapeyron relation. Right. So that's how physical phenomena can be described by using the Maxwell's relations. Okay. So this is the phase diagram of water. Okay. Now we can have different kinds of questions. Like here, what it is said is that the ratio of adiabatic to isothermal elasticity is given as gamma. Okay. Which is also the ratio of Cp by Cv. How do we prove that? Right. So one thing is we know that gamma is given as Cp by Cv. We also have to prove that it is equal to the ratio of adiabatic to isothermal elasticity. Right. So how do you do that? First, let us see what is the definition of elasticity, adiabatic elasticity and isothermal elasticity. So the expression of elasticity is given as V into del P del V. Okay. Now, if it is adiabatic, S is kept constant. If it is isothermal, then T is kept constant. So these are the expressions of your adiabatic and isothermal elasticity. Right. Now let us take a ratio of the two. Okay. So once you take a ratio of the two, how did you go from this step to this step? If you spend some time, you would see here we have del P del V at constant entropy. Here you have del P del T at constant entropy, del T del V at constant entropy. Right? So how did you get here? So this is nothing but an expansion, right? So you can write del P del V as del P del T into del T del V, right? That is what is being done here. Just expanded it in terms of two differentials, two partial derivatives, right? Now, for each of this, you can have different Maxwell's relations. So you can substitute them. If you substitute them, you would get an expression like this. So this comes out of the Maxwell's relations. But now, how do you go from this step to this step? Right? How is it possible? Let us think for a while. And just giving some time so that when you see the video and try to solve it. So whenever you're seeing the video, it's like I would always tell that try solving it yourself as well. Okay, don't just look at it passively. So I'm just giving you some time so that you also try to work it out. So from here to here, sorry. So from here to here, you have just expanded it. Del P del V is del P del T into del T del V. Again, del P del V is del P del S into del S del V. Why have you chosen this combination? Because you want to use the Maxwell's relation, right? So you have taken those combinations and now you can rewrite them in terms of the Maxwell's relation. That's what you have done. But now how do we go from this, second last line to this line? What have we done here? All right. So here what we have done is look at this section separately and look at this separately, right? For both this, pairs, here P is constant, here V is constant, right? So now you can use your, the relations of partial differentiation, and you can rewrite this term as del S del V into del V del T, which is nothing but del S del T at constant pressure. Similarly, this becomes del S del P, del S del P into del P del T. So again, del S del T at constant volume. Now you can understand if you multiply T both in the numerator and denominator, what do you get? T ds by dt at constant pressure, which is nothing but dq dt at constant pressure, which is Cp, right? And again, you get T ds by dt at constant volume, which is nothing but T ds by du dt at constant volume, which is Cv, right? So that means that's equal to gamma. So you could actually prove that the ratio of adiabatic to isothermal elasticity is nothing but the ratio of the two specific heats. Okay. So for this kind of questions, see, this is a very fundamental relation for so like this relation you should remember, and you should have a basic idea of how one defines elasticity. Okay. Rest, once you know how to use the Maxwell's relations and the basic ways of dealing with partial differentiation, you can solve this kind of question. Okay. Okay. So these are the different, relations that have gone into this step, right? Okay. So just mark. Okay. Now the next question is that the equation of state for a substance is given as V is equal to some relation between R, T, pressure, some constants, and temperature pressure, right? So this is your equation of state. And it said that find how Cp varies with pressure at constant temperature. So what you have to find? You have to find del Cp by del P at constant temperature. Del Cp by del T, del Cp by del P, how Cp varies with pressure at constant temperature. Del Cp by del P at constant T. That's what you have to find, right? So given this, how do we start with this kind of question? Okay. I'll give you a couple of minutes to. Okay. V is provided. You have to find del Cp by del P. Okay. What is the definition of Cp? Where do we start? Okay. V is given in terms of pressure and temperature and certain constants. See, we want to find Cp. What is Cp? Cp is TdS T ds by dt constant pressure, right? So you want this. What you know is you know V in terms of T and P. So if you have to find this, you have to somehow in this expression, you have to somehow bring a derivative with respect to pressure, right? Because you have to find a derivative with respect to pressure. So what do? You do a derivative with respect to pressure. Okay. So charge. So you have to find here you have derivative with respect to temperature. You need to do a derivative with respect to pressure. So that means there will be a two derivatives involved, right? So you know this this is already there. What if you multiply with a or what if you do a differentiation with respect to pressure? What do you get? Right? So now here for this part, okay, you can try to use the Maxwell's relation. And there, the important point to note would be that because you're dealing with entropy, entropy is a state constant. So the order of differentiation will not matter. Okay. So what I mean by that is del S del T at constant pressure. Okay. And then doing a partial derivative with respect to pressure is same as doing a partial differentiation with respect to temperature of del S del P at constant temperature. Understood? So these two are interchangeable, right? Now we know the Maxwell's relation for this term, right? So del S del P at constant temperature is given as minus del V del T at constant pressure. So we know this term here. Now we have done a derivative with respect to temperature. So it becomes a double derivative with respect to volume, of volume with respect to temperature, right? So because you have to find a relation of Cp as a function of or a derivative with respect to pressure, you look at the initial description of Cp, there dt is involved, right? And you know from the question that you need to do a derivative with respect to pressure. So that means you need to have a relation where you are looking at entropy and you are doing two differentiations, one with respect to pressure, another with respect to temperature. And then choose a Maxwell's relation which makes use of one of this, partial derivatives. And we know this is the one. So that tells you that you have to start from this this Maxwell's relations. Okay. And then because in the Maxwell's relations, you have a derivative with respect to pressure, you do the next derivative with respect to temperature. Okay. Then because it's an exact differential, so again, this point is coming, you can interchange the order of differentiation. Okay. This term becomes a double derivative with respect to temperature. And this is nothing but, so multiply both sides by T. So this becomes del Cp del P at constant temperature, right? So this is what you have to find. So once you know this relation, so this relation by itself is actually very important. Okay. Del Cp del P at constant temperature. How does it relate to this? This entire form, this relation is very important. Now, if we go back to the question, we have to find this thing. The expression of volume with respect to pressure and temperature is provided. Okay. Right. So what do we have to do? We have to do a double derivative of this expression with respect to temperature. That's what this right hand side of this equation is telling you, right? So that means this is your expression of V now. So do del V del T and then do del square V del T square at constant pressure. So this is your expression. T temperature times this term will be giving you how del Cp del P changes with temperature, which now goes as T to the power minus 4. So for this thing, your answer would be T to the power minus 4. Right? So that's how this kind of questions has to be addressed. So it's important how we got to this expression. First, start with what you have to find. Okay? What are the different variables with respect to which you have to do the differentiations? Okay. And what is your state function that you're working with? Then choose the correct Maxwell's equations accordingly. Use the identities of, exact differentials or cyclic relations or reciprocal theorem, okay, to rearrange the terms according to your question, and then put in whatever information is already provided in the question. That's the basic rule. Okay. Yes. Here it says that derive the given expression which determines how CV varies with volume at constant temperature. So initially we found del Cp del P at constant temperature. Now we are finding del Cv del V constant temperature. Okay. So how do we do it? I'll give you a couple of times to just, couple of minutes to just think about it. It will be a process similar to what we have. Where's my marker gone? So similar to what we have done here. You have to choose the Maxwell's equations correctly based on what is your term that you want to find. Okay, but the process will be similar. So try to work it out. Right? How do we find del Cv del V at constant temperature? Okay, what is the Maxwell's equation that we should start with? I'll give you some time to think. So whenever you're looking at this video, you know, I would always suggest that try to, solve it actively, try to solve the questions. Because for this kind of questions, it's not difficult, it's just getting used to, this equations and differentiations and derivatives. It's just getting used to this. Okay, so try to solve. Okay, so let's again try to solve it. Okay, so here we start with the definition of CV. How do you define it? You define it as T ds dv at constant temperature, right? Now here on the right hand side, you can see you have a double derivative with respect to of pressure with respect to time. That means what is this anyways telling? Here you have one derivative with respect to volume, keeping temperature constant. Here you have two derivatives with respect to temperature, keeping volume constant. That means if you start with this form, okay, you have to then do a derivative with respect to temperature. That's how it has to go ahead, right? So that's what you have to find at constant volume. That's the thing. And now because this is a exact differential, you can interchange the order of differentiation, right? So this tells you you have to start with this form, right? Also here, because you have del square p del t square, that is already telling you that the form on the right hand side should be del p del t at constant volume, right? And here you have to start with something like del S del V at constant temperature. So now if you take a derivative with respect to temperature here, okay, how will it look like? So this is your Maxwell's relations, okay? And now you take a differentiation with respect to temperature, keeping volume constant, okay? So here it will become del square P del T squared constant volume, right? And interchange the order of differentiation. So it becomes del V of del S del T at constant volume. This is a state function. Okay. Because it's a state function, the order of differentiation is immature. So this always remember. Okay. So that already proves your point, right? Because now if you just multiply on both sides by t, what will you get? This is your t into del square p del t square at constant volume, which is your right hand side. And the left hand side, what does it become? It becomes t. So if you put in t here, sorry. So if you have a t here, right? So t ds dt at constant volume. This term would be your CV, right? So what you are getting here is del V of CV at constant temperature, which is again your left hand side. So that's how you can prove it. So the only thing that changed was based on what was the equation, you had to choose the starting Maxwell's relations accordingly. Okay. This is another question which says that the equation of state of a thermodynamic system is given where you have a relation that relates pressure with temperature, volume, and certain constant. Okay. And the internal energy of the system is also specified where it's a function of volume and temperature. Okay. Now we have to find the values of B and N. So you have an expression of U. This is the form. One sec. So while you have an expression of internal energy, you have an expression for pressure in terms of B and T. You have to find the values of B and N in the expression, right? So where do you start? Because internal energy is so clearly specified, you can start with the first law, right? Just give it a thought. Okay, how to address this question. So the hint is start with the first law, write ds, which is differential of entropy, right? Write ds using partial differentials of u, okay? And use the concept that S is an exact differential. So based on this hint, I give you a couple of minutes to try to solve. It's a little involved, so I'll give you some time. So let's see. So this is the answer, okay? Let's see how to get there. So you start with the first law, okay? So start with the first law. Now express ds as in terms of u and v, okay? So you can write it as you can expand du again, okay? By writing u as a function of t and v, right? So you're writing du as del u del t into dt plus del u del v into dv, okay? Just expanded it, and you had another term just given as p by t dv, okay? Now what you do is you take this term, just rearrange the term, okay? So take this here and this term along with like collect the dt and dv terms separately, right? So what is this giving you? This is giving you ds in terms of dt and dv, right? Now from our basic understanding of ds, and you know we know, so you can always write ds as, so if you now consider s as a function of t and v, right? If you write s as a function of t and v, so you can always write ds as, del S del T into dt plus del S del V into dt, dV, right? So now this term is nothing but what you have here, right? And this term is nothing but what you have here, this entire term, right? So you have an expression for ds dt and ds dv. Now, because S is a exact differential, we can do another differentiation, okay? And the order of differentiation won't matter, right? So what it means is that you can do del t of del S del V, and that should be equal to del V of del S del T, right? So from there you would get a relation which is like this. Okay. So you're already getting a relation, right? So if you compare the left and right hand side, you would get just compare the power of temperature. So from here you would get a value of N, and from B you can, like, by comparing this you can write B in terms of A, right? So that gives you this answer. Okay. So for this kind of questions you have to choose a state function, some exact differential, so that you can use these ideas of multiple differentiations. Okay. Okay. Now, in stretching a rubber band, Tg is given. This is the Gibbs free energy, and it is of this form. Okay, so if there is a rubber band, so there is some force dl term here. Okay, vdps dt. Now, which of the following is true? That's the question. Now, for this kind of questions, you should be careful about looking at the options provided. Okay, so in all these options, you can see that pressure is always constant. Okay? That means you don't need to actually care about this term. Right? So now if you just look at these two terms, right, just setting the P to 0, okay, dP to 0, sorry, you can just look at now these two terms, right? I'll just one second. Basically, along with the minus sign, I mean this two term, right? These are the two terms that matter. So what you can write? You can write S in terms of, you know, del G del T at constant L, and you can write F at as del G del L in terms of as at constant temperature, right? That gives you S and F in terms of some partial derivative of G with respect to T and L, right? And then here you can see that there are all these relations that relate S and F or V, right? So that means you have to find derivative of S or derivative of F or derivative of V, things like that, right? So V will anyways not come because you're getting rid of this term here. So that means once you write S and F in terms of derivatives of G, you have to do another derivative. Okay. And there again you have to make use of the fact that that G again being a state function is an exact differential. Okay. So consider P to be constant, find S and F in terms of partial derivatives of G, and then G is an exact differential. So that's the hint. Okay. So I'll give you another couple of minutes. Let me know the answer. Okay. Try to solve it. I'll discuss the answer after that. Answer is the two. See how. So considering P is constant, you write dg as minus sdt plus fdl. Okay. So comparing with the basic definition of dg in terms of dt and dl, you write del g del t at constant pressure and L is minus S, and del G del L at constant pressure and temperature is F, right? Now G is a exact differential, so you can do another derivative and the order would not matter. So del square G del L del T will be equal to del square G del T del L, right? So use that, okay? So do a derivative with respect to L here and do a derivative with respect to T here. What do you get? Del S del L minus of that at constant pressure and temperature is equal to del F del T at constant pressure and L. Okay, so that's your first option that you had. Okay, so this very idea of choosing the correct thermodynamic potentials, looking at their differential form, using the definitions of partial derivatives, okay, and using the fact that each state functions are exact differentials and the order of differentiation does not matter, will be very useful in addressing this kind of questions. Okay. Now, this is another question which says that a gas obeys the equation of state. Okay, so the equation of state is provided to you and has a heat capacity CV independent of temperature. So del CV del T at constant N is 0. Okay. Now it says that find the Maxwell's relation involving del S del V. So, how do you address this? See, the Maxwell's relation is independent of what equation of state is provided, right? That's always true, right? So, if you want to find the expression of del S del V, you can start with the right thermodynamic potential, and that will give you the answer. Okay, Tn is 0. Okay, and you want to find del S del V. Okay, so you can start with the Helmholtz free energy, and it has a form like this, right? See, because n is constant, you have taken dn to be 0. Okay, so then there are two variables that are there in your picture, right? So you are doing a derivative with respect to v. So v is one independent variable, and the other one which remains constant during the partial derivative is temperature, right? So you need some thermodynamic potential that can be written in terms of T and V, right? So that's why you chose, like we choose this, you know, the Helmholtz free energy, okay, and it can be written in terms of the differentials by using this relation, right? So what does this tell you now? This tells you that now again you can write del S del V at constant T, that is temperature, and N is equal to del P del T at constant V and N. So this is your Maxwell's relation that you wanted to find. So for this question, if you are asked to find a Maxwell relation involving certain quantity, look for what are the different independent variables with respect to which you have to, you know, uh, define the partial derivatives, right? So in this case, you are doing a derivative with respect to volume, keeping temperature constant. So here the two variables are V and T, and that will tell you which thermodynamic potential to choose. Like here, you are choosing the Helmholtz free energy. Once you do that, rest is same. Okay, again using the concept that they are state functions, exact differential, doing double derivatives, and rest process is the same. Okay. Okay. Now the next part of the question says that by calculating dE, show that E is a function of T and N only. Okay. So you consider dE as a function of T and V, and you have to show that it does not depend on volume. Okay. It just depends on T and N. Okay. So how do you do that? See, you can write ds in terms of dt and dv, right? This is something we just started with. So de is equal to tds minus pdv, and then you can expand ds in terms of t and v. Okay, you can use the Maxwell's relations, okay, which comes in here, right? And collect terms with respect to like dt and then dv. What did you get? You got e as a function of t and v. That's what you were supposed to find, right? Now here you have to use the equation of state. This is the equation of state that is already provided in the question, right? Because you need to find this term, right? So to find this term, use the expression of the equation of state, which tells you that del p del t at constant v and n is nothing but p by t. So this term gets cancelled, right? So what is this telling you? This is telling you that del de is only dependent on this term. Okay. So you can see it just depends on v and n. Okay. And it does not depend on uh, t and n, and it does not depend on v. Clear? Because this dv, the entire coefficient in front of dv has gone to zero, right? Just by using the equation of state. So the use of equation of state comes after you have written the expression of de, not before that. Okay. Because that's what you have to be careful about, that choose the independent variables based on what are your choice of partial derivatives that you want to deal with. So here you wanted to write e in terms of t and v, right? So that's why you had chosen this form, so that you get an expression involving dt and dv for de, and then use the equation of state. Okay, because the coefficient of dv in front of dv goes to zero, so basically there is no dependence on volume. Okay, that answers your question. Okay. Now the next part of the question says that if I go back, so that gamma, which is Cp by Cv, is this value which is independent of T and V. Okay. How do we show that? Okay. So I would always urge you that whenever you're seeing the video, please solve it. Okay. Try to solve along with why as you see the video, also try to solve it. Okay. So gamma equal to Cp by Cv, which is given as this. This is what you have to show, right? Now you know the definition of Cp, you know the definition of Cv, right? Cp is dq dt at constant pressure. You can rewrite dq using the first law, dE plus pv. Okay. Now, since E is a function of temperature only, and this is something we just found out, right here, it just depends on temperature. So because E is a function of temperature only, del E del T at constant pressure will be the same as del E del T at constant volume, right? And del E del T at constant volume is nothing but Cv. This is the definition of Cv, right? So while Cp is given by this relation, Cv is given as del E del T at constant volume, which is also del E del T at constant pressure. So that means what do you get? You get Cp is equal to Cv plus this term, T del V del T at constant pressure. Right. Now you want to find del V del T at constant pressure, and that you can get directly from the equation of state that is already provided, right? This is your equation of state. So from here you can actually find del V del T at constant pressure, right? And substitute it there. So when you substitute here, what do you get? You get del V, my marker. So del V del T at constant pressure is n kb by p. That comes from equation of state. So if you substitute it here, you get a relation between Cp and Cv. Okay, and this is independent of T or V. It's a constant quantity, right? So now what you can do is, gamma is Cp by Cv. So divide both sides by Cv. So gamma becomes 1 plus n kb by Cv, which is independent of T and V. Okay. So that's how you can answer this kind of questions. Now, the fourth section tells by writing an expression for E as a function of P and V. Initially, you had written E as a function of T and V. Now it is saying that write an expression of E as a function of P and V or otherwise, so that an adiabatic change means dq is 0, right? That would satisfy the equation p v to the power n minus p into v minus nb to the power gamma equal to constant. So that means for an adiabatic change where dq is 0, you have to show that this holds, right? That's the question. Hmm. So dE is CBDT, right? Now you can always use the equation of state to write dt in terms of P and V because you want to write E in terms of P and V, right? So you just change dt in terms of P and V. Okay. So this is what you get. So now you have an expression of dE in terms of dV and dP. Okay. That's the first thing you have to do based on this question. Now adiabatic condition means dq is equal to 0. So if you put dq equal to 0 and use the first law, okay, so that means dE plus PdV is equal to 0. dE is nothing but CVdt, which is the first this expression, right? Right. So dE plus PdV goes to 0. Okay. So that's the expression. You have used the adiabatic condition. Now it's just rearranging and looking at simplifying this equation, right? Rearrange all the terms involving dp and dv, separate it out, okay, and then divide by this term here. What do you get? You get dp by p plus gamma into d of v minus nb by v minus nb. So it's like you are separating the variables. Okay. Now this is equal to 0. This already tells you that that means ln p v to the power n p into v minus nb to the power gamma becomes constant. It's just using the logarithmic condition, right? So yeah, so that's how you can solve this question. So the first point is because you have to write E as a function of P and V, you have to use the equation of state here to go from dt to dv and dp. Okay, that's the first step to solve this question. Okay, rest follows. Rest is just using the condition that it's an adiabatic change, so dq is 0. Okay, and then simplifying the equation. That's it. But this is an important decision to make as to do this substitution. Okay. Yeah. Now, if you remember in the last class, we did discuss about the concept of equilibrium and the process of reaching equilibrium or approaching equilibrium. And we talked about the direction of time. We said that whenever the system gradually tends towards equilibrium, it tries to maximize its entropy or minimize its internal energy. Right now, based on whatever system you're looking at, your expression of which potential to choose, you know, what would be your expression of generalized force, generalized displacement, all of this will change. But in the most general form, okay, way, thermodynamic systems in stable equilibrium can be described by this condition that you have here. Okay, where is my uh, this marker? I always lose. I don't know why. Yeah. So this is the general criteria for stable equilibrium. So equilibrium can also be, unstable or neutral, right? We're talking about stable equilibrium. And for that, this is your condition, the general most condition. Now, by using this, okay, there are different important inequalities that come up in the derivatives of the state functions or thermodynamic potentials. Okay, so these are the some of the important relations. Okay, so we'll try to start from this, general expression which is here. Okay, start from here and find these. Okay. So till now, when we are talking about thermodynamic variables, we are talking about systems in equilibrium. Now we are talking about the criteria that talks about, you know, the state of reaching equilibrium, or what are the conditions uh, or inequalities associated with it. Stable equilibrium. So the stability criteria is given as this. Okay. So now what you can do is you can consider a system where the generalized force is given as pressure, generalized displacement as volume. So that means we get a form like this. Now here, if you take n as constant, so dn, this term goes to 0, you are left with just this inequality, right? Now for constant volume, what happens? Again, this term goes away. So what you get is del S del T greater than equal to 0. Right? Now suppose you want to find how from here you can get to an expression which involves the uh, the internal energy, right? That means you need a relation. From this point, you need a relation that relates S and T with the internal energy, right? If that is the case, you can also relate it to Gibbs free energy or Helmholtz free energy, that we'll get there. But suppose for now, you want to describe the stability condition in terms of the internal energy. So that means from here, from S and T, you need to find an relation with E. Now, if you know, if you remember, we had already been discussing about this relation which comes from the first law, right? Like using both the first and second law. So it tells us that del S del E is given as 1 by T, right? So this is the relation which relates S, E, and T. So what do? We write delta S as del S del T into delta T, okay? And then you have another delta T. Now this is a positive quantity. So that means for this to be greater than equal to 0, your del S del T at constant V and N should be greater than equal to 0, which tells us del T del S at constant V and N should also be greater than equal to 0. Now what is del T del S? So here you can replace T by del E del S, right? That's the relation. Now once you do that, here you have got a double derivative with respect to of E with respect to entropy. And from this stability criteria, we could actually write an inequality that has to be satisfied by this double derivative of double partial derivative of internal energy. Right? So similarly, you can look at different combinations of, like, you can find a relation for del square E del V square. You can find a relation for uh, you know enthalpy, for free energy, for all of it. Okay, just you have to choose, which of these terms to look at. Okay, and then you have to choose at uh, what should be your what do I say, what should be the based on what state function you want to find, what should be the so out of S and T, suppose here, whether you should actually look at derivatives of entropy or you should look at derivatives of temperature. So that would depend on what you have here, right? If you have T here, then you should, you know, write delta T in terms of, like, do a derivative of temperature. Okay. So that's how you have to choose your dependent and independent variables. For example, if you are asked this, to find this del square E del V square, right? How do we get here? So what you can do is, so for this case, you choose delta S to go to 0, delta N go to 0. So this is your form. Now you can write del V as del V del P into delta P. Why did you choose to write this? Because here you had a V, right? Okay. So now you can just substitute, okay, in this expression. Substitute with the expression of delta V, which again tells you that from here that del V del P is less than equal to 0, which means del P del V is also less than equal to 0. Now here you can write P in terms of the derivative of internal energy. Why have we chosen internal energy? Because that's where what we wanted to prove, right? So based on this, you have to choose the relation. Now, once you have done that, you get this expression. Right. So the same thing can be done for, all different kinds of, I mean, s- all the different thermodynamic potentials. You can do that. Just trying to remove the marks. Yeah, so suppose if you have to find this, I'll give you a couple of minutes, try to solve for this maybe. Or this, like choose two and solve. So, I mean, suppose if you want to write in terms of the free energy. So what do you do? See, you want to find this, right? So that means in your expression, you can take V and N as constant. You can just work with this pair, right? And there you have to write for delta T, substitute delta T. So now you write T as a function of all these terms. So you can write delta T as del T del S at constant volume and N into delta H squared, right? This term is already greater than 0. So that means del T del S should be greater than equal to 0, which again gives you greater than equal to 0. So see, this is already the same expression that you initially had here as well, right? You also had it here, del S del T greater than 0. So del T del S greater than equal to 0, right? You already had this expression. But there you did a substitution based on what thermodynamic potential you're dealing with. That was internal energy. Now you're talking about Helmholtz free energy. So the expression will change accordingly. So here you again know ds dt greater than equal to 0. So look at the differential form of the gives or Helmholtz free energy for this case. And we know that del F del T at constant V and N will give you minus of entropy, right? So now you can substitute this here. What will you get? Del square F del T square less than equal to 0. So that's how I've got to this expression. Okay. Now, similarly, you can also have, I mean, if you want to write double derivative with respect to volume, you can take T and N as constant and just work with this pair. substitute delta V, okay, then you get del P del V less than equal to 0. Here you do a substitution based on this, right? Del F del V at constant T and N should be minus P. So using that, put this expression, like put the expression of P in terms of derivative of F, and this is what you get. So the same thing can be done for Gibbs free energy or enthalpy or for different thermodynamic potentials. Okay. So like this is how you do it for enthalpy. This is how you do it for, the other inequality for enthalpy. One is with respect to entropy, another with respect to pressure. Okay. And the same thing, same process goes on for even Gibbs free energy. Okay. So that's how the initial criteria of the stability criteria can be written in terms of different different inequalities involving different uh, partial derivatives of the thermodynamic potentials, and these inequalities talk about how a system approaches stable equilibrium. Okay, so we discussed about Maxwell's relations, which talks about the relations between different thermodynamic variables, different state functions. Okay, and how to use those relations to find different quantities. Those were inherently based on the fact that whenever you're defining a state function or defining a thermodynamic variable, you're talking about systems in equilibrium. We're talking about equilibrium thermodynamics here, right? But then we also discussed at the end about how a system approaches equilibrium. Okay, what are the different criteria to approach stable equilibrium? How does the different thermodynamic potential vary in that transient phase? Okay, that is also there. Okay, there are certain inequalities that they satisfy. So that's something which we discussed today. Um, I think that's it. If there are any doubts, feel free to reach out. Okay, so yeah, thank you. Yeah, just waiting. If you have any of you, if you have any doubt, you can reach out to me in the next class or write to me. Okay, thank you.